I will say, hey, you know what? On my machine, I have an instruction called vector instruction. How many of you have heard of this thing called vector instruction? A few hands. Okay. What is a vector instruction? You raised your hand. Okay. Okay. What's a vector instruction? One register, I forget, I missed.
You have like vector registers. The rate is 64 bits. You can divide it into 32. You can load two ends, do computation on both at the same time.
Yes and no, they're more. What's a vector instruction? Correct. What's a SIMD instruction? Don't tell me what that's a VFX instruction. Correct. Let's say I want to do V sub I equal to A sub I plus B sub I. Okay. This is one addition. What if I say, look, I have 4 add units, and let's say we go with RISC model, so that I can only add registers. So this will be loaded, this will be loaded into register, add both of them, I store it in another register. But like our friend said, let's say I have a register or a big register or a vector of registers, a vector or an array, think of it, where I can load 4 of these and put them in one register, B also 4 of them in one register. Then it will do the addition of these 4 operands, 4 A's, 4 B's in parallel, and store them in 4 C elements. You can specify in registers, or depending on the architecture, you can put it back in memory, but the idea is the same, that can I do small operations like addition in parallel? Can I do small operations in parallel? And the vector instructions cannot work on a group of such arbitrary things. So I can do a vector addition on this, maybe on this also, but I'm just telling you. So I can do vector operations. Those set of operations are fixed. Let's say addition, I can do parallel addition. It's not that I can do parallel addition of many things. There is a size. Let's say I can do 4 vector integer additions in one go. Okay, maybe 4 floating point vector additions in one go. Correct? So what I am saying, I want the compiler to zoom in only on this guy. Okay, how do I do it? I say, hey, you know what, focus on this, focus on this separately. So loop distribution helps me focus on one of those. Okay, once I have done loop distribution वगैरह, I may get some code that looks like this, right? The same loop I took the first loop, this is the loop. As I was telling you, I have a vector instruction that can work on, let's say, 4, it can do 4 additions in parallel, but only 4 at a time. But this is only one addition. You know what I'll do? I'll do loop distribution, I got this, now I'll do strip mining and get this. Now pay attention, here I had 1024 additions, here I have 256 these for loops. It so turns out this whole for loop can be replaced with one single vector instruction, more or less. There may be some minor loads here and there, but given this for loop, it's a very straightforward one-to-one mapping to a vector instruction. Okay. So you can have a low level instruction that can add, you give the address, starting address of A, starting address of B, right? So what I can do, so I want to do A sub I plus B sub I, correct? Maybe what I can do is I can create a new address for this. T1 equal to address of A sub I, T2 equal to address of B sub I, okay, and then give to the vector instruction, boss add starting from T1 and T2 take 4 elements, first of T1, first of T2, T1 sub 2, T2 sub 2 and so on, right? Other T1 0, T1 1, T1 2, T1 3, and then store it in let's say similarly T3 equal to ampersand V sub I, I'll say store it in T3, vector add. Okay, sometimes it may take few more operands, but the idea, this is not any specific machine instruction. I am giving you a what's the right word, a generic view. Give the starting address of one operand, starting address of the second operand, number of operations and the destination. Basically what it means, this inner loop is gone. This inner loop can be replaced with a powerful, importantly parallel instruction. Look at the gains. If I run this, how much time I would have taken here? Let us say each addition is taking 1 unit. This would have taken 1024 units of time. How much time will this take? 256 plus slightly more, because the vector instructions are slightly slower than individual adds, but not as slow as 4 times. Okay. So this will be slightly more than 256 units of time. This is called as vectorization. When can I vectorize? I can vectorize if, here is simple condition, there are more complicated conditions. The simple condition is if the iterations are independent. If the iterations are independent and I know the axes are contiguous. It's important the axes are contiguous. ये नहीं कि this is 1, that is 3, that is 25, that is 27, right? Let's say I am accessing something like V sub I equal to A sub some function I plus B sub some function I. I won't be able to vectorize. Okay. Let us say I have a function called Fi. I don't know what this function is. So I'm adding the, let's say Fi returns 3 for I equal to 1 and Gi returns 5 for I equal to 1. Then for V1 I will add A3 plus B5. Let's say for I equal to 2 it returns 16 and 21. Then I have to add A16 and B21. So they are not contiguous. The compiler cannot tell whether I am accessing contiguous elements of data or not. Then I cannot vectorize. For me to vectorize, I should be doing some operation on contiguous elements. Okay, fine. We normally vectorize only some specific operations, not any arbitrary functions. So sometimes we also use this notation. It's called vectorization or SIMDization. SIMDization, and sometimes we use this notation also. Same thing. It says is from I to I plus 1, I plus 2, I plus 3, I plus 1. It need not be always same. I could do A sub I equal to B sub I plus C sub I plus 1. That's okay. They are independent. It need not be always same. But on the other hand, let us say I want to have A sub I equal to A sub I minus 1 plus 1. Then there is a problem. If I depend on my previous value or next value, and I'm kind of both of them if I'm depending on. So if there are dependencies, it will be difficult. What we will see next is how to compute these dependencies. Okay, but before that, let us convince ourselves that such SIMDization or vectorization can be extremely effective. Okay. Again, if it is a for loop, it's easy to see it. In a while loop, I won't be able to do strip mining. I won't be able to do SIMDization. Fine. Okay. So this is some set of loop optimizations we looked at. Unswitching we looked at, tiling we did, unrolling we did, reversal we did, loop invariant code motion, loop inversion, loop interchange, loop fusion, loop distribution, strip mining, vectorization. Right? What I plan to do now is we have been talking about, hey, there is a dependence. We'll try to see how we define these dependencies, how we will get some names, some nomenclature, so that, and some procedures on how to compute these dependencies. Again, I'll keep it brief though, but yes, that's what we'll do. Here is one more interesting part. Let us say I have this loop. Okay, this is something we have not talked about among loop optimizations, but let us say I want to parallelize the loop. Not paralyze, parallelize. Okay, if I want to parallelize the loop, what does it mean? If I can run each of the iterations in parallel. I have a multi-core machine. So this box probably I will have some 16 cores. That box has some 8 cores, right? Even the cell phones these days have many cores. Wouldn't it be nice if I have a loop with many iterations, they run in parallel. That way they can take advantage of the available cores, correct? How do we parallelize? Basically, can different processors or cores or hardware threads, depending upon your system, can they run different iterations in parallel? If you give a for loop, the assembly code to the machine, it will not run it in parallel. It will not. इसमें से कौन सा मेरा है? Sorry. Right. If you give just assembly code, it will not run these iterations in parallel. The compiler has to tell the assembly code should have instructions, run this in parallel, run this in parallel. Who does it? Humans can do it, or the compiler will do it for you, right? Let us say I have this loop. A sub I equal to B sub I, C sub I equal to A sub I minus 1. can I parallelize this loop? That is, can the right question to ask ourselves is it okay for different iterations to run in parallel? Look at this way. I am writing to a sub 1. In iteration 1, I think, yeah, in iteration 1, I am writing to a sub 1, correct? In iteration 2, I am reading, correct? Iteration 2, I am reading a sub 1, isn't it? If I equal to 2, I am reading a sub 1. In I equal to 1, I am writing to a sub 1, correct? If this was to run in parallel, what would happen? I may be, in iteration 2, I may be reading the a sub 1 written in iteration 1 or the old one. Am I making sense? Let me try again. If I parallelize the for loop, then iteration 1 and iteration 2 can run in parallel. That means they can happen in any order. There is no, I am not fixing the order between the operations of iteration 1 and iteration 2. Within iteration 1, let's assume they happen in that order. Within iteration 2, let's assume they happen in the order of the program order. But between iterations, let us say I am not specifying any order. Then what can happen? Pay attention. In iteration 2, I am reading a sub 1. In iteration 1, I am writing a sub 1. In the serial code, when it is not parallelized, in iteration 2, which value of a sub 1 will I read? The one that we have written in iteration 1, correct? But if it is parallelized, there is no guarantee. Why there is no guarantee? Because there is no guarantee that iteration 2 is happening after iteration 1. When, see, there is one cardinal rule of parallel programming. When you say these two can run in parallel, don't assume, oh no, mostly this will run before this. No. You have told they will run in parallel, that means don't assume any ordering between them. Okay? As a result, if you parallelize, this will lead to wrong results. Wrong results, because the serial program says it should happen in this order. The parallel, if you parallelize this loop, the semantics will change. Correct? There are three types of dependencies that we normally talk about. You write, you are a statement after him, you read. We will call it as read after write. In architecture, you would have studied this. Read after write, raw dependency. In compilers, we call it as flow dependence. Okay? Or true dependence. Arey, ye kya hua? Right? We call it as flow dependence or true dependence. In architecture side, you might have heard it as read after write dependence. Okay? So there is a write that is happening in iteration 1. There is a read which is happening in iteration 2. In the serial program, iteration 1 should execute before iteration 2. So in the serial for loop, there is a flow dependence from iteration 1, this statement, to the second statement of iteration 2. I will write it, if this is S1 and this is S2, I can say S1, okay, and S2, there is a flow dependence. I'll write this with, I thought I switched off. No, I didn't switch off. Yeah. So there is a flow dependence from S1 to S2. Okay. What I am saying, if I am reading in certain iteration, in the previous iteration I am writing it. So I can write it as in iteration S2, this is a flow dependence. The left side is a right, the right side is a, not left, right side is a read. The LHS is a write. So S1 writes, let's say in iteration I minus 1. In the iteration I am reading it. Okay. We have, remember, whenever we are talking about dependence, we are always talking about dependence from past to future. It's never future to past. Okay. It's always from past to future. So the left side is always past. So the iteration on the left side. So this whole thing, right, statement comma iteration, this is telling me not just S1, it says S1 of the I minus 1th iteration, right? I can have some other types of dependence as well. First one was flow dependence, second is anti-dependence. Okay, anti-dependence is also called as anti-dependence is write after read. Okay, write after read, as in, let us say I am writing to X, I am reading X, okay, or if you like arrays, maybe I'll just make it as y equal to X sub I and somewhere down the line X sub I equal to blah. So this is a read, this is a write. We say there is an anti-dependence from the statement S1 to statement S2. There is no flow dependence from here to here. This is an anti-dependence. Pay attention, this is an anti-dependence, right? Write after read. Let's see if we had one example for anti-dependence here in the previous slide. Did I? Yeah. Let's look at this one. What dependence do I have between AI and AI here? Huh? This is read after, right? Flow dependence or true dependence. Same iteration. So I will write it as S1 I, S2 I. Okay? Correct? That is for A. What about B? There is a dependence. Is there any dependence between these two? It's not a dependence that we normally care for. It's also a dependence. It's called as input dependence. Okay, but we mostly don't care about. So we'll mostly focus on the other three dependencies. So here I don't have an example. Let me write an example for. Do I? Which one? It's not a dependence that normally stops us from doing loop optimizations, right? So if you look at this loop, so ignoring input dependence, that is both are reading, we want at least one of them to be right. Is there any dependence between iterations of the second loop? Is there any inter iteration dependence? Not intra, inter. Okay? Is there any inter iteration dependence here? No. So I can parallelize this loop. This loop I cannot parallelize. Okay. No dependence, parallelize. With dependence, you cannot. You have to do, sometimes you can eliminate dependence, sometimes you cannot. That's a separate issue. Some types of dependence, not all types of dependence, but yeah. So if you look at, this we have already talked why with the dependence I cannot parallelize. Okay, let's look at this graph again, sorry, this code again. I can represent the program or the loop by focusing on its iteration space. Let us say this loop goes from, you're a savior, madam. Sure. Thank you. I will keep, let us say this is n is 6. Okay. If n is not known, that's a separate issue that can also be dealt with, but let's say I have n equal to 6, then I'll have one node per iteration. Okay. And then I will, on each node, I will have a label, something like I equal to 0, I can say I am reading A0, I am writing, I am I equal to 0, what am I, kuch to gadbad hai. It is not the same, I think this is correct. I starts from 1, right? So I am reading. No, I don't think, I think I messed up. I got the code from some other, this code is not matching with this. Right of, this should have been 1, na? Correct. Yeah, this is I equal to, this should, okay. There are multiple, give me a quick sec. Yes, you know what I did? I copied the wrong code here. Chalo koi nahi. I copied the wrong code. I equal to 1, I equal to 2, I equal to 3, I equal to 1, I am reading A sub 0 and writing A sub 1. No, yes, that's right. Right? So I can say on this I equal to 1, I can have a label. I can keep basically additional information, what it reads, what it writes. For each node, if I have multiple statements, sorry, by I equal to 1, this is iteration I equal to 1. I just kept, I mean, see, if I don't have the loop, let us say I don't have the loop, I have 6 statements. I'll keep 0, 1, 2, 3, 5. If I have 6 statements within the loop, for each loop I can have different inside loop I can have many statements. I'll just list all the statements S1, S2, S3, S4. For each one I can no, this number is not exactly matching n, this is n. So what I'm saying is that I equal to 1. You want to keep a labeler, okay, it will read A0. Here it's reading A1. I equal to 2. See, basically what we are trying to do is represent the loop, right? By saying, hey, I have these many statements which are executed in different iterations. What is being read, what is being written in each statement. Then I can say, aha, if at in iteration 1 I am writing, in iteration 2 I am reading. This is a, what type of dependence is it? True dependence, flow dependence, because this is happening first. Look at this code. Let's say I have a sub a of I plus 2 comma a sub I, okay. In iteration 0 I am writing a sub 2. The same a sub 2 I am reading in iteration 2 at a distance of 2, okay. Oh, now I realize what has happened. I'll do quick change for my own convenience, don't worry. The previous correction, the code was this code. Yes. Now I realize where I made the mistake. Yeah, the code was this one. For this code, I plus 2 and I, okay. In iteration 0, I am reading 0 and writing to a sub 2. In iteration 1, I am reading a sub 1, writing to a sub 3. Iteration 2, reading a sub 2, writing to a sub 4. Correct? I can write it like this along with, here there is a write to a sub 2. So there is an edge. So this is my iteration space, iteration 0, iteration 1, iteration 2, iteration 3. I can say there is an edge from iteration 0 to iteration 2, iteration 1 to iteration 3, right? Now we will introduce a new term, this dependence. We are saying there is a dependence from iteration 0 to iteration 2. What's the distance? Distance is 2 iterations. In iteration x, if you are doing something and something in iteration x plus 2 is dependent on it, I say the distance is 2, right? Are we fine so far? So it's called as the dependence. How much distance do we have? Wow. Thank you. It's enough to burn my tongue. Thank you. Okay, so the distance is 2, right? But we call it a distance vector. Why is the vector coming into picture? Let us say I have a loop nest. Maybe the next example should show a loop nest. Dependence cannot be backward, it's always forward. You cannot have the dependence is always from older iteration to a newer iteration, or same iteration to same iteration. I cannot have from maybe I understand your question. Your question, you will appreciate it if I write a nested loop. Let us say I have code like this: for I equal to 0, I less than n, I plus plus. For j equal to 0, j less than whatever m or n, whatever, j plus plus. Okay. Let us say I have a statement. I am writing to a sub ij. Okay. Equal to a sub I minus 1, j minus 1 plus 1. Okay. So if I'll make it 1, otherwise this becomes problematic. Okay. At iteration I equal to 1, j equal to 1, I am reading a sub 0 0, which is written in the, which should have been written before. So if I write, let's focus on I equal to 2, j equal to 2, let's say, or maybe just for my sake 2 and 3. Okay. Then what I am writing is dependent on what? Which was written in, if this is the right, in this iteration I am writing to this, which is dependent on something which was written in I equal to 1, j equal to 2. Okay. So what I am saying, this right, the right in I equal to 2, j equal to 3 depends on a read. When was this value written? Go back. This value was written when this, no wait, did I miss something? No. In 2, 3, I am reading the value a sub 1, 2. When was a sub 1, 2 written? In iteration I equal to 1, j equal to 2. So there is a dependence from, let's say, from the same statement. If I am writing in I comma j, there is a flow dependence. Whatever I am writing now, right? So there is a flow dependence from this to this. This was written here, this is read here, right? To write a comma 3, a 2 comma 3, I am reading this. So there is a true dependence there. So I will write it as I plus 1, j plus 1. No, I'll mix it up slightly just for you. Let us say I have one more loop, one more this thing. A b sub I, j I am writing here, equal to b I minus 1, j plus 1. This is more interesting. Okay, pay attention to this. Okay, I am writing in iteration 2 comma 3, I will be writing b2 3, and whose value depends on b1 4, depends on b1 4. So now what is the dependence? So you will write s1 I comma j, let's say there is a flow dependence. I am writing in this I plus 1, j minus 1. The left side is always smaller. The first one is important. This, see, this is showing what? Two loops. This is showing loop 1, loop 2. loop 1, loop 2. I am saying in loop 1 when I am writing in iteration I, comma j, it will be read in loop 1's iteration I plus 1 and loop 2's iteration j minus 1. Right? Remember, okay, which iteration comes first, I comma j or I plus 1 comma or this one, which comes first? This must come first because this is a smaller number, isn't it? So this comes first, then this comes. There is a flow from here to here. Take some time with your friends. Convince. I mean, this points here, this points here. Sometimes what I wrote it this way. You will also find sometimes they will write it as the other way around. This one they will one may write it as I minus 1 j minus 1 flow S1 I comma j. This and this are, I mean, you shouldn't get distracted. How come? 2 sub? No, it is m. The iteration. I have n iterations. How many iterations does, when I say 2 rows are done, these 2 rows, this is 2 times n plus 3. That is the iteration number for this. I mean, if you want to serialize all the iterations, and this would be 1 times n plus 4. The m and n. Photo से कुछ नहीं होगा. You can take a photograph, but discuss with your friend. I am here. We are not talking anything complicated. Okay. Or is it not visible? Ayyo. Oh, you can zoom in on your photograph. Smart. Very smart. Just check with your friends, no? Please. Check with your friends that you are able to see the dependence. Friends. We are going into more math now, more examples, less examples, more math, but yeah. Huh. Yeah. deep. There are k loops, and so this is the vector for one such loop nest, right? For some value of I1, I2, I up to Ik. I say this vector is less than equal to some other vector J1, J2 up to Jk. That means this instance would have, this iteration would have executed before this. Okay? It's a loop nest of k loops, all deeply nested inside. Now let me ask some examples. So I am writing the same symbol in all the places. Which of it is true? 2 comma 3 is less than equal to 2 comma 3. True? 2 comma 3, this iteration happens before 1 comma 2. No. 2 comma 3 happens before 1 comma 4. 2 comma 3 happens before 4 comma 1. But this one is, but 2 is smaller than 4. Good. 2 comma 3 less than 4 comma 5. Slides. Right. Thanks. Thank you. What's your name here? You have been helping us. I don't even know your name. Vani. Thank you, Vani. Okay, yeah. And what about 2 comma 3 less than equal to 4 comma 5? True. Right? So when we are now saying we will order the iterations by looking at their iteration vectors. Okay? So now we know how to order these iteration vectors. Okay? So the dependence can only be present from a previous iteration to a future iteration. I cannot have dependence from future to past. Okay? Right. When we say there is a flow dependence, we can write it precisely like this at a distance of 2. Okay, there is a dependence at a distance of 2. There is a dependence, this says at a distance of 1 comma minus 2. What does it mean? Next iteration of I, but j minus 2. Okay? Plus 1i minus 2j. So first non-zero entry must be positive. I mean this one, the first entry here has to be positive, first non-zero entry. You can have, it's possible that I1 equal to J1, I2 equal to J2 and so on. And then there is some element here which is non-zero. There is some element here which is non-zero. This guy must be less than this guy, equal to. Okay? Let's make it less than. This guy must be before this. What will I write if I have code like this? A sub f of I equal to A sub g of I. Here I don't know which iteration depends on which iteration. Okay. If I have some code like this, I don't know. I won't be able to calculate the distance in such a case. I won't be able to calculate the distance in such a case. I can mark it as infinity, saying that some distance is there, I don't know. Okay. The distance vectors sometimes are summarized as direction vectors. Instead of keeping the exact distance, all I want is the direction. 2 comma 1, 2 comma minus 1, I'll mark it as plus minus. I'll forget the how far it is, but I'll just keep the क्या कहते हैं more or less this is the way the direction is, right? 0 comma 3, I'll mark it as, sometimes it's written as 0, sometimes it's written as plus minus. Okay. And 1 comma minus 2 as plus and minus. To say, here is a simple test for parallelization. We said they should be independent, right? So, if there is a non-zero entry, that means there is some dependence. If all entries are zeros, then there is, if my dependence vector or direction vector is all zeros, what does it mean? There is no inter-iteration dependence, isn't it? 0 means I only depend on myself. 0 means I only depend on myself. I am not dependent on anyone else. If I say that I am not dependent on anyone else, and every iteration for every statement in the loop body, I say, oh, it's independent. It only depends on itself. What does it mean? I can parallelize the loop. So no loop carry dependence. So if I have no non-zero entries, means no loop carry dependence. If I have some non-zero entries, what does it mean? There is some dependence. Yes or no? Okay. Now let's get back to yesterday we studied loop interchange, right? Let's look at this loop. For I, some for loop, for j, I plus 1, j plus 2, a is equal to a sub ij. Now the distance, let's look at the distance. I am writing in certain iteration which is read later. Okay. You will see, so the distance is both positive. It's not, I don't care it's 1 comma 2 or 100 comma 200, it's just plus plus. Okay. That means I am writing in iteration I comma j, I am writing to some other iteration which should happen later. Okay. Now, but both are positive. Both are positive. So what is it? Let me see if I can draw a 2D matrix. If I have a 2D matrix, in iteration I comma j, I am writing, let's say this is iteration I comma j, I am writing to the, I am reading a sub ij, but I am writing which one? I plus 1, I plus 1, j plus 1, I am writing to this element. Okay? Do you see what I am saying? There is dependence. Is there dependence or not? There is dependence. I mean, I am writing to, across iterations, I am writing something that you are reading. But now look at it. Currently, I want to do row wise. I want to change it to doing column wise. when I am doing this iteration, I am writing this. Okay. Am I using this? I mean, if I interchange the loop, will this change? I mean, will the value change? Look at in the first, in the original code, I would do row 1, row 2, row 3, row 4. When I am doing row 4, I am writing to this element, row 5. Correct? Now if so while, and only after that, so I have, after processing this, this I comma j, I will come to write this. Okay. Let us say I do column wise, I do first column, second column. When I reach this element is in the same state as before, it has not been updated. I am not reading any updated value. Previously, in the original code, before interchange, I am reading the unupdated value. After doing column wise, I am still reading the unmodified value, unupdated value. So if it is both plus and plus, interchange is okay. If one of them is minus, then there is a problem. Similarly, say instead of plus, let's say I have a 1 comma minus 2. The dependence was 1 comma minus 2. After transformation, it will become plus minus will become minus plus. ये नहीं चलेगा. Okay. But if it is plus plus, after transformation also it will remain plus plus. Okay. Okay. Look at one more. Let's look at fusion. Let's say I have this 2 loops. I want to fuse them into a single loop. In these 2 loops, there are 2 independent loops. Is there any dependence between loop 1 to loop 2? What type of dependence is it? I am writing here, I am reading here. This is flow dependence. Okay. I want you to, on your notebook, fuse the 2 loops and tell me what happens to the dependence. So my code will become for I this statement, this statement. What happens to the dependence? How? In iteration, let's say I equal to 2, I am writing A sub 1 and reading A2. So I am reading A2 first in iteration 1 and reading A2 and writing to A2 in iteration 3. So I was about to write on this. So in iteration 2, I equal to 2, I am writing to, sorry, I am reading A sub 2. In iteration 3, I am writing to A sub 2. So this is an anti-dependence. So this is not okay. You cannot combine this. I mean, we have to be careful when we are combining also, right? So if I, no, maybe this is safe to do. Is it safe? I think. This is okay. This is okay. But let's be aware that the dependency is changing. Sometimes it may lead to. I won't be able to combine all the time. Let's look at this code. A sub I equal to A sub I minus 1, B sub I equal to A sub I. Okay. I won't be able to parallelize this loop because of the dependencies. However, if I distribute the loop, distribution is okay, and then this can be vectorized after that or even parallelized. Dependencies. Again, if there are no dependencies, I mean no forward. See, when I distribute, it's okay if there is a dependence forward. If there is no backward dependencies, it's okay. I'm writing to this AFI, and if I make sure that all these A sub i's are written first, then I'm reading them, there is no issues, right? So distributing it is okay, but if I parallelize it, what can happen? It may so happen, sorry? Correct. So for A2 I should have gotten A1, the updated value. But if you parallelize this whole loop, A2 may get the old value of A1. So there is dependence, so you cannot parallelize this loop. But if you distribute the loop, I am still okay. Anyway, so the point is, when there is dependence, we need to be careful about distribution, parallelization and all that. How do we compute dependence? Let's say I have an array A which is accessed. Let's say I, J are my I is the current index. Let's say A is accessed like this. A1, B1 are constants. A1I plus B1. So somewhere in my loop, I have A1I plus B1, and somewhere I have another axis of A2J plus B2. Okay, where I and J could be computed based on the index variable. It could be, this could be like I plus 1, this could be I minus 2, where I is the index variable. For example, in our example, this is I minus 1. So at one place I am accessing with I minus 1, some other place I am accessing with I. Okay. So the point is, if I am accessing an array with some expression A1I plus B1, maybe I could, let me write, let's say I have a for loop, I am accessing 2I plus 3 equal to something, and I am reading A sub 3I plus 1. Okay. Now I am asking, is there dependence between these two? That is, does there exist an iteration in which I write to an element which is accessed in some other iteration, the same element being accessed in another iteration? What does it mean? In some iteration, let us call it as I1. So in some iteration I1, 2I1 plus 3 matches this element in some other iteration, let's call that as I2. So I want to ask, is there a possibility that 2I1 plus 3 is equal to 3I2 plus 1 for some values of I1 and I2? Is it possible? Do you see why we are asking this question? Anyone? I am saying, let's say some iteration I1 I am writing, some other iteration I am reading. I want to ask, is it possible that 2I1 plus 3 and 3I2 plus 1 are same? If they are same, what does it mean? They are referring to the same array element. Can they refer to the same array element? How do we know? I equal to, for I equal to 2, this will become 7, this will become 7. Correct? Okay. So what does it mean? We solved this equation. We solved this equation and did something extra. We found the value of I1 equal to 2, I2 equal to same is it? Okay, so this means they have a intra-iteration dependence. This means they have a same iteration dependence. Is it possible that I have a solution for I1 not equal to I2? That would be inter-iteration dependence. See, to parallelize or not, I want to check whether there is inter-iteration dependence. Right? Across iterations is their dependence. So that means I1 not equal to I2. Do I have a solution where I1 not equal to I2, 2I1 plus 3 equal to 3I2 plus 1? Absolutely. If you want to draw these two, do they intersect or not? In this case, they won't. Except for the same I1 equal to I2, they won't intersect. So that means now you can say there is no inter-iteration dependence, you can parallelize these iterations. Right? Let's change this slightly. Hey, wait, why did you say, what about I1 equal to 5 and I2 equal to 4? Huh? Let's look at this. I1 equal to 5, I2 equal to 4. So they do intersect in such a case. I didn't see all the points, of course. So there is a value of I1, there is a value of I2 for which they intersect. So what does it mean? In iteration 5 I am writing something, in iteration 4 I have read the value. So there is an anti-dependence there. More importantly, so there is an anti-dependence. Iteration 4 I have read, iteration 5 I am writing. So there is an anti-dependence. Yeah, this became 5 and 4. So for 5 and 4 there is a solution, correct? Let me change the program slightly. Let us say this was only till 4. Then does this, do I have a solution for this? I want a solution for this equation for two constraints. One, I1 not equal to I2. If I want to look for inter-iteration dependence. Second, I1 less than equal to the max value here 4, I2 less than equal to max value 4. So for this loop, do I have now inter-iteration dependence? No. It's possible that for some other values of I larger than 4, there is a dependence, but not here. Correct? So we are looking for two things. If there is a integer solution, remember we are looking for integer solution only, integral solutions. for this equal to this, and I1 is less than loop bound, I2 is less than loop bound. Sorry, J here, I am writing I and J both are less than loop bounds. Right? So one can solve these linear Diophantine equations. There are many different ways to solve. What's the time? Huh? Okay. Okay. So here is a very simple dependence test. Okay. It's called a GCD test. It says dependence is possible. Okay. Only if GCD of A1 A2, GCD stands for greatest common divisor, GCD A1 A2 divides B2 minus B1. If it doesn't divide, what does it mean? No dependence exists. When it is true, it doesn't mean there is a dependence. Dependence is possible, only this condition is there. So what I will do this GCD test, check if there is dependence or not. If the GCD test fails, that what does it mean? No dependence, pakka, right? If the GCD does not divide B2 minus B1, then happy, no issues. Okay. This is pretty fast, this testing, but it's very conservative. Many times we won't get the right answers. There are stronger tests. I leave it to you for reading. There is a test called Banerjee test. Okay, very popular test, very powerful test. Read it yourself. Okay, but let's have a quick recap of what we said. Loop optimizations depend a lot on dependence test, dependence evaluation. Dependence can be seen, can be studied as, I mean, some dependencies we want, there should be no dependence at all. Sometimes we say no, positive dependence is okay. Sometimes we say no, I mean dependence only intra-iteration is okay, inter-iteration not okay. Depending on the loop optimization, I may require a different dependence requirement. And how do we capture this dependence? By distance vector, by direction vector, right? And whether there is dependence present or not, when you have arbitrary expressions. Remember, this is still linear. What if it was a more complicated expression? It becomes much more difficult to identify whether they have dependence or not, right? Yeah. GCD test will tell me whether, what will GCD test tell? Dependence is there or dependence not there? The GCD test can only give me guarantee that dependence is not there. Because if it fails, I know there is dependence not there. If it succeeds, there is no guarantee that dependence is there. So GCD tells me the case where there is no. Okay, any questions? Okay, if there are no questions, what we will do, I think tea has come, right? We will have a quick tea, come back quick because we will give an assignment to do. What is the assignment? In the IMOP framework, you will be implementing loop vectorization. So yesterday you did loop unrolling. Some of you might have felt slightly, what's the right word, unsatisfied. Hey, we did unrolling, but we don't know how much gains we got. You could have actually tried it, generated code you can compile and run. So today what we are giving you is another slightly different piece of code. Can you just, it's the same code I had sent, or you have made many modifications? Same program with a new demo file. Okay, we are giving you a new demo file. Copy the demo file to the directory that you care for. Okay. Before you start your assignment, on your machine, do the following. on your machine, do the, okay, ये क्या हो रहा है? I can't see what I'm doing here. Okay. On your machine, so the file name, what have you kept? T1 or changed it? Vector. Okay. There is a file where vector underscore example dot C. So run this code with the following options: minus O3, okay, minus F no tree vector. I think that's right. Okay. There is also a readme file, but yeah. So run this. You and give a minus. This we call as base. Okay, this is your baseline. So then run your baseline code. Run time baseline. Okay, it will tell you how much time the baseline code takes with O3 optimization, but no vectorization. You are telling GCC not to vectorize anything. Okay. Now you do the transformation and you get another code. Okay, your output. Let us say the output is. Let us say the output you generate is in a file called vector. But in README, what file does it say? Vectorize.c, let's say. Okay, let's say the output you generate is vectorize.c or vectorize.i, doesn't matter. Okay. Then do the same thing again. Okay, now instead of calling it right. So what we are doing, we are optimizing the code, asking GCC to process it. The way we optimize, the details are there in the README file. Okay, we will be telling GCC, for boss, don't do any analysis. I am telling you, you vectorize. Okay, it will vectorize it for you, and then you can run the, not baseline. Sorry, you should run the. We still do. We are telling GCC, don't use your brains, listen to what I am saying. Right? Because GCC, you will see in the test file, there are many loops. We are telling you to specifically pick a loop to vectorize. Because of time limitations, we are not asking you to do dependence testing. You can assume that someone has done the dependence testing and yeah, told you that it's you can vectorize it. Okay, so in the input file we have given a label to a loop. You just have to find that loop, do some transformations. What transformations do you have to do to vectorize? Strip mining. Mark the inner loop for vectorization. Okay, is that fine? You have to strip mine and mark the inner loop for vectorization. You are not vectorizing it. You are telling GCC boss, vectorize it here. Strip mine and give a annotation that, hey, this is to be vectorized. There is a pragma you insert. The specific pragma is mentioned in the README. Is that right, Mitesh? The pragma name is mentioned. Oh, you have given it as a hint, is it? Oh, perfect. Okay. All right. Have a good tea, and then we will meet. Okay. You have sent me an email, no? I will send you on your in the WhatsApp. Huh.
in command also.
Yeah. Because you are telling GCC, don't use your brain. Whatever I am telling you, only do that.
But then you're also saying to use the
GCC say, I am telling GCC, don't use your brain, listen to me. So it will do it for you. Huh? Vectorize it, sorry. हाँ कोई बात नहीं यहाँ we'll just write it so that if someone looks at it, no, they don't make a mistake. T के बाद is this correct? Guys, we have a dedicated TA, a highly dedicated TA who says he wants to give you a quick. This thing will do that. So he wants to run through the steps once. Just quickly do it. It won't take much time. Just delay